So, welcome all to the course of Fabrication Techniques for MEMS-based sensors. So, particularly from a clinical perspective. So, it's the week one, and um, so I am Udiptya from IIT Madras, and so I have completed my Bachelor of Technology in Biotechnology, and then I'm currently pursuing my PhD at IIT Madras. And the areas where I'm working is on fiber optic biosensors, and using this platform to and also on some nucleic acid amplification tests. So something like the PCR and all such techniques are called as nucleic acid amplification tests. So those that is also one of the area that I'm working, and also nanomaterial synthesis and characterization. So before this course, I had been a TA for two other courses. Uh, One was fundamentals of micro and nano fabrication. So it was completely on the fabrication stuff, on a nano and micro fabrication. So all that also I think is included in this course too. And like just before this semester, I was a TA for the course research methodology in natural science, uh, kind of a general course that is needed by all the scholars for uh, basically to understand the research methodology. So during the course of the during this course of this problem solving sessions, if you come up with other questions or any doubts, you can reach out to me in this email ID, and I will try to answer your doubts as and when it's possible for me. And yeah, just reach out to me, and then we can discuss the things here. Yeah. The only thing is, NPTEL has told us to essentially restrict ourselves uh, to not discuss directly the questions of the assignment, the current assignment that is going on. Apart from that, you all can discuss like anything. Yeah, anything is possible. So, uh, the first week was on introduction to microengineering devices. So, one important thing that we learned is what is MEMS technology. Yeah? So, MEMS means micro electromechanical systems, and it is a process technology. So, we also heard this word of process and recipe. The process technology used to create tiny integrated devices or systems that combine mechanical and electrical components. So this microsystems or microengineering has a lot of other domains too, and depending on, so these are the different components or different classification of MEMS. Yeah, so you can see that mechanical and optical makes optomechanics. Mechanical and electrical means MEMS, and optical and electrical is optoelectronics, and all together is kind of MOEMS. So there are a lot of things and a lot of differences in between these different sectors of microengineering too. But all in all, this MEMS essentially is consisted of four broad components. These are microsensors, microactuators, microstructures, and microelectronics. So, can anybody tell what is, or like, can anybody define kind of what is sensor, what is actuator, what is the role of electronics, and what is the role of structures here? Anybody? No? So it's okay to speak up. It's all because it's only us here, so it's, you don't need to be think a lot here actually. Yeah. So okay. So sensors means it essentially senses the things, and uh, it essentially transform one form of energy to another form of electrical output, which can be measured. Yeah, that's the function of a sensor. So we have micro sensor, micro actuators means that essentially transforms one form of energy to a force, yeah, to a moving force. So that's actuator. So depending on one electrical output, you can essentially move something. That's actuator. Electronics essentially is when you have some device and you need to make some decisions out of it depending on the output. There comes the importance of electronics in it. Yeah, the decision making, or the, yeah, the counting, decision making, detection, all that are controlled by the microelectronics. And then so basically here is where the that all the codes and all the programs, all the logics go in. And then the microstructure, essentially the structural part of the MEMS. Yeah, how these MEMS are, the different structures, the different uh, the sensors and all the actuators and microelectronics, all are in the micro regime. So the structural senses, microstructures. So all this comes together and makes a micro engineered device, or particularly a MEMS device. So uh, going on, some of the benefits of MEMS technology. So these are some of the benefits. Maybe there are a lot more, but essentially we discuss some of them. So the three main thing was miniaturization. So when we miniaturize a thing, we essentially save material, save power, and or also they are in these devices we have faster time response compared to their bulk counterparts, and essentially better performance. Second point is integration. So we can integrate this MEMS into some other ICs, integrated chips or other systems, and reduce system size. So you can put one system on top of another. So you can reduce the system size, system cost, and you can connect interconnected different interconnected systems together. So yeah, the save adapters, save interconnection wires, and so on. So essentially you have a compact design of a, yeah, of your device. And also batch fabrication. So as we go on understanding the different aspects of fabrication, we will understand that how these devices are made, and how can they be made in a scale, uh, in with contrast to the bulk components, like how we make them. Yeah, here we can make them in a bulk, in a different, like a wafer can have a lot of devices made together. That's what it is. So you can have cheap and disposable too, using different kind of, now polymers are also there. So you essentially can uh, print your devices on those polymers, and essentially, and now there are a lot of techniques of paper fluidics, and a lot of such integrations that essentially make also environmentally sustainable solutions for these technologies. So there comes the factor of cheap and disposable. So in scale, the scale we also produce also helps in uh, getting a cheaper kind of fabrication technology for the same. Yeah. So these are some problems that we can discuss now. So I've just put the problems, and the thing is, I will show the question, and then I will give some time for you to answer. You can answer both in chat, and also through voice. Yeah, everything is okay for me. And then we will discuss it together. Yeah. And after we complete the problem discussions, we can go to any doubts that we have, and then we can discuss it in the class, and then yeah, then it's the end. Yeah. So this is the first question. The term IDE in this course stands for. So you have heard this word a lot, yeah, in this during this course. So yep. So yeah, these are interdigited electrodes. So essentially how this looks is, uh, you have electrodes. So yeah, and then you have these are kind of interdigited electrodes. So what is one of the characteristic is they have what kind of resistance? What is the resistance between these interdigital electrodes? You all can't recall. So um, the interdigited electrodes will have their micro. No, micro heaters is something different. So micro heaters is kind of a bit different. So interdigited electrodes will have infinite resistance, yeah, because they are not connected. Yeah, so they will have infinite resistance between them. But essentially, we provide some samples or some. So uh, the application, as in whatever we use it for, like if we use it for example, sensing the different electrical properties of a cell. Yeah, so whenever we put the cell on this, then we see, okay, then there is some changes in the resistance or not. So there we can see, okay, then we have infinite resistance. Then after we put a cell here, maybe then there may be a flow of current. So that's, then we reduce this resistance. Yeah, so that's how sensing happens. So that's the purpose of this. And otherwise the micro heaters is something that have a coiled structure. Yeah, and essentially the purpose of it was to have larger length, and as a result they can provide more heat. So that's what is microheaters. Okay, then we go to the next one then. Yeah. So this is the second question, that immunotherapy is a therapy that will activate your immune system. Is the statement true or false? How? Okay, so most of you are telling true, yeah. So yeah, can anybody tell how does it, with example maybe? Yeah. So okay, so when we give immunotherapy, in immune system we have different kinds of immune checkpoints, yeah. So essentially you provide some drugs uh, which can bypass, or which can drugs which can attack these checkpoints. So you have the one that that have been discussed in the videos, yeah. uh, Anti PDA. So that essentially blocks the checkpoint on the T cell, and that's why the T cell activates, and essentially you have more number of uh, uh, CD8 or killer T cells in your body. So essentially boosting your immune system to act against the cancer, or any whatever therapy you are undergoing, or the patient is undergoing through. So yeah, so it's blocking the blocking immune checkpoints. So that's what it is. So yeah, it's true. So yeah, the smallest change in input which a sensor can detect and express as output is called resolution. Okay, others? Okay, so essentially all these are called as sensor characteristics, yeah. These are called as sensor characteristics. Can anybody name other sensor characteristics, like apart from all this? Yeah, linearity. Yeah, range. reproducibility, repeatability, transfer function. Like what do you mean by that? Response time. Okay. Then accuracy, yeah, precision, nice. So essentially, yeah, the answer would be here, resolution. Yeah, hysteresis. Nice. So that the smallest change in input which a sensor can detect and express as output is called as resolution. So what's specificity? So it's like I make a sensor for COVID, yeah, but essentially it should only give a response to COVID virus, yeah. It shouldn't give response if I have a common cold or influenza or any other lung infection or respiratory based infections, yeah. So that's what is specificity. So my sensor is specific to the disease or to the condition or uh, to the to the to the thing that I am basically sensing. And then resolution is smallest change. What is sensitivity? Change in output to change in input. Yeah, perfect. So that's sensitivity. Or somebody also tells about the slope of it. Yeah, the sensitivity. That's the sensitivity. The slope of the calibration curve. Then we have linearity. So what's the linearity? So if you have a sensor, maybe here it is the concentration of a compound, yeah, and then you have a signal here. So your signal can be like this. So this is the linear range, the linearity, and range is essentially the range where your sensor can detect. So what's the difference between reproducibility and repeatability? Why are they like two terms? So repeatability is checked in terms of one user or testing in the simulation. Yeah, so essentially when we do um, a measurement, yeah, essentially provide we do it in um, n number of times, yeah, more than 3 times, or as such to get a statistically relevant data. So to do it in the same sensing setup or same measurement device or same conditions essentially is repeatability. And reproducibility is, so you report one sensor, yeah, I try to reproduce it in a sense, and if it gets reproduced or if it gets the same kind of response whatever you are getting is it referred to as reproducibility. And the response time is how is it defined? Yeah. So, so in a sense, it is defined as around like the thing you are taking, the time taken by sensor to react to an input. Yeah. So they have in some, basically in some, I think most of the literature they say is 95% of the signal, whatever time it takes to essentially give the 95% of the signal is taken as a response time. But yeah, it varies essentially. Then what's the difference between accuracy and precision? Actually, there are some nice graphs, nice uh, photo about this accuracy and precision and this. So, yeah, if I can recall, so these are some darts. Yeah. So so these are two conditions, yeah, three conditions essentially. So this is high accuracy, highly accurate, and highly precise too. This is, because this is far from the true value, it is low accurate and but highly precise. Yeah. Then you have this condition in which it is low accurate, and all the points are also differently placed, so low precision too. So this closeness of all the values is defined as precision, and how far it is from the true value is what is the accuracy. So yeah, then the hysteresis. Yeah, then what's hysteresis? Hysteresis is essentially the direction dependent, to understand the direction dependent property of the sensor. So essentially if there are some uh, dynamic sensors, yeah, so like the temperature sensor. So if, so for example, this is the temperature sensor, and you go up the sensor, is this is the response. But when you come the sensor, whether this is the same kind of response, or you get some kind of like this, or some kind of like this. Yeah, so that's the hysteresis, the difference between the direction, like when we are increasing it or when we are decreasing it, whether it is different or not. So that's what is hysteresis, the direction dependent property of sensor. Yeah. So yeah, kind of we discussed all the sensor sensor characteristics. Yeah. So we'll go to the next one then. So what is the most common shape of commercially available silicon wafers? Can I do? Okay, yeah, it's circular essentially. Uh, can anybody tell what's the like kind of a size essentially? What mostly people use or what is commercially used? The size ranges essentially. Yeah. Mm-hmm. Yeah. Correct. Circular with some flats, as in. But in mostly in industries or such, yeah, they start I think from 4 inch to 4 inch is quite rare though. 8 inch and 12 inch. So yeah, so those are some kind of the size ranges that basically they operate in. So you also learned about VOCs, yeah. So what are those? Yeah, those are volatile organic compounds. So some examples of it are the different organic compounds, yeah, acetone and ethanol, yeah, etc. Yep, petrol too. So yeah, this is the next question. An oxide layer is deposited on a silicon wafer before deposition of metal layer. This is usually carried out to limit the effects of bulk silicon wafer on the conductivity of metal film. Is the above statement true or false? So why is it true? Yep. Can we tell why is it true? So what is a silicon? Silicon is a what kind of material? Yeah, perfect. Semiconductor. Yeah. So what could be the reason then? What happens in semiconductor is you have very little gap between the conduction band and the valence band. While in metal or conductors, it is kind of this gap is not there, yeah. And in insulators, the gap is what it is called as Eg. So there is a if anybody of you remember, there is something called as Fermi level. Anybody remembers about this? Energy level between conduction and valence band, yeah. But what is the significance of this Fermi level? Why is it so important? Yeah, because there are infinite number of levels between. Uh, it's used as a reference energy level, like, but it should be have a like specific use case, yeah, or a specific definition. Highest occupied energy level. Uh, okay, but like how like highest occupied energy level? So, so you are kind of partially correct. So it's the highest occupied energy level, yeah, uh, that the electrons can exist at absolute zero, yeah, or the 0 Kelvin, whatever. So this is kind of the Fermi level you can consider. So whenever you have a silicon wafer and then a metal component on it, yeah. So whatever, if you want to only rely on the electrical properties of the metal, then you essentially, if you put electrons here, yeah, you put electrons here. So if you do not, if as the silicon is a semiconductor, you will essentially lose some electrons in this silicon too. So essentially, you won't get the full potential of the metal, or full whatever use or whatever sensing you would like to go through the metal. Some kind of signal would be lost by the due to the silicon. So essentially, what you do is we have a passivating layer of some insulator, yeah, silicon dioxide. So essentially, then you won't get this kind of losses, and essentially all the electrons will move through your metal. So you won't lose the conductivity of the metal fluid. Yeah. Well and good. Okay. So there was a question on uh, wafers and wafer flats. So what the shape of the wafers? Yeah. So this is some kind of question. Then on this wafer flats. So wafer flats signify certain information about the silicon wafer. The angle between the primary and the secondary flats of a silicon wafer indicates that. So first is what's primary and what's secondary flat. So you told that a wafer is a circular size and circular in shape, yeah. So what's the primary and secondary flats? The primary and the secondary flats, yeah. That's what we are discussing. Crystal orientation. Okay. So there it can be multiple type. Yeah, that's possible. So the primary and secondary flats are essentially, the primary one is the bigger one. So the bigger flat is what is called as a primary. Yeah. And the smaller one, if there is called as a secondary flat. So it's telling that if these flats of a silicon are indicates what. So one answer was crystal orientation. So is there any other answers, or should we discuss it? So this can be multiple correct, yeah? This is multiple correct. Multi. Let me see if it doesn't. Multi correct question. So essentially there is another option too, or any other options too, which are possible. No? Should we discuss them? So yeah, so here we say that there are different kinds of flats, yeah. So it can have two things, is that there are the angles, yeah. There you see the different angles of it. So depending on the angle, you have essentially the crystal orientation. Yeah, one of you have answered crystal orientation, and also the dopant type, whether it is N, P. So here you see, yeah, if it's in 180 degree, the primary, there is 180 degree of variation, you have primary or then you is 100 plane N type. In case of 90 degree separation, it's 100 P type, and respectively on 45 degree, it's 111 plane, and if it doesn't have a secondary plane, secondary flat, then it's 111 P type. So that's the kind of a universal notation how these silicon wafers work on. So the answer will be this two. Yeah. So yeah. So what's the difference between bulk machining versus surface machining? So you all can explain through a example too. So it's not like you have to be have a definition based answer. So it can be based on understanding of your own, and then you can elaborate it also. Somebody uh, would like to answer it? So, okay, so we will discuss that then. Removes large volume of material to shape the workpiece. Is bulk machining. Yeah, perfect. So, it's like when you have a silicon wafer, and so I have this kind of silicon wafer, and here we have some kind of stops. So this can be from silicon nitride or something, but essentially we etch it. Yeah, when we etch it, essentially remove this part. Yeah, and so what we are left behind is some kind of silicon. So this is bulk machining. Yeah, but when we have some kind of uh, uh, experiments that happens on the surface, for example, uh, you want to make a cantilever. Yeah, so how will you make is you have a silicon wafer. Yeah, and then you want to make you will put a sacrificial layer. Yeah, so this is the structural layer, and this is the sacrificial layer. So when we etch only this sacrificial layer, what we will be left behind is a silicon wafer and a free supported structural layer with no support in between, in beneath, on its beneath. So beneath it, so essentially we have only machined something on the surface, so that's surface machining. Yeah, so these are the two kinds of, here we are removing bulk of the material and here we are removing it from the surface. So that's the method of surface machining. Yeah. So how are cantilevers? So we had just discussed about cantilevers. Yeah, please. You want to discuss something? Yeah, Pavitra, you have raised your hand. So yeah, can you please tell me surface layer? Okay, okay, yeah. So any machining that happens on the surface of the material is called as surface machining. So here is another example that of surface machining that we have told. So here what we are removing is, we are removing a sacrificial layer, yeah, from the surface of the silicon. So in such conditions, we are not removing the bulk of the material. So therefore we are calling it as surface machining technique. But essentially you will also gain like also know about these methods of different kind of, like different kinds of surface machining and bulk machining in the coming slides of fabrication essentially. But just to give you a gist of what the methods are essentially, because they were mentioned in the video, so I just thought, okay. So yeah, just kind of a example based answer, but yeah, more when you learn about the fabrication it will be more clearer, and also learn the technical aspects of the machining too. Yeah, but yeah, just I have to mention here, I just missed the word micro machining. Yeah, because yeah, we are not talking about we are only talking about the micro scales, so yeah, pardon me for that. So surface is happening at surface essentially, and this is the bulk of it. Yeah, that's the basic thing. Yeah, should I go ahead? Yeah, perfect. So yeah, we also saw how, like, a crude way how cantilevers are can be made, but yeah, how are cantilevers useful for breast cancer diagnosis? So can anybody tell how this can be used? And yeah, it can be different than what the videos or other stuffs also has, the course has. So yeah, anybody can tell about this, because yeah, cantilevers are used a lot on sensing. That's all. Yep, answers please. So yeah, so in the course we learned that these cantilevers are essentially very good. So what are these cantilevers? These are essentially free floating, uh, yeah, free standing like this. Yeah, yeah. Then these are free standing. So these are very good at understanding the because these are very flat. Then if it you apply any force on it, so it essentially will bend. Yeah. So these are very good at detecting the stiffness. So essentially we have piezoelectric materials here, which essentially uh, transfers this movement into electrical output. Yeah, then we can sense the different stiffness of different cells also. So essentially when we have a cancer cell, usually a cancer cell the microenvironment of a cancer cell or the stiffness of a micro of a cancer cell will be quite different from the normal cell. So if we understand such characteristics, we can use our cantilever based system to diagnose the breast cancer. Another idea was is to also you can also in some literature you also can find that they coat these cantilevers using some kind of receptors. Yeah, so this can be some antibodies. Yeah, which are specific to the breast cancer cells, and then whenever the cell comes and sit on it, it will undergo a bending. Yeah, so that bending can also be quantified, and you can also diagnose breast cancer according to it. So these are kind of two methods. There can be a lot of other methods too.
how this cantilevers can be useful for breast cancer diagnosis. Yeah, so you all can think about some other methods, or some, like, in some conditions, like apart from the piezoelectric materials. Yeah, there can be also approaches like where we have this cantilever, and here we have a laser. Yeah, and here we have a mirror, just like how if anybody has used IAFM. Yeah, and then the laser, essentially this is a mirror, and there we have a detector. So whenever this moves, like it moves, the cantilever bends, this laser and this deflection will change, and depending on this change they can understand the bend of it and detect it also. So here we don't need a piezoelectric material. So such there are some other methods too, how these cantilevers can be used, and how there are different systems essentially, uh, how it is used for this kind of diagnosis, or essentially breast cancer diagnosis in particular. Yeah, so if there are doubts you can ask. Yeah. Okay, so I think I can go to the next, maybe. So, during these days, you might have learned about this painless microneedle. So, in which I think one of the vaccines for COVID had also come for this microneedle based injections, and also some very important inventions were made in like now I think it is ongoing, but for uh, providing injections on eyes. Yeah, because eye is a quite uh, sensitive part of our body, so to put injections on it directly, and like putting it through the conventional syringes, it's quite painful. So now this microneedle based concept has come, and uh, so it's kind of a biomimic design. So we have mimicked it from a biological being. So you have to tell which you think can it be, and it would be very nice if somebody can tell why it is painless. So yeah, so before discussing, so essentially when we have like we let's understand why it's painless. Yeah, so why it's painless is essentially these microneedles essentially have this kind of spikes in it. Yeah, and the drugs are essentially mounted on this, and what is there is uh, the pain receptors or the nerves essentially are in this layer. So essentially it doesn't cross this pain receptors, and essentially that's why you don't feel a pain, while the bulk uh, needle based ones are with a syringe is inserted uh, like to through the pain receptors. So as a result you feel this kind of pain. So essentially these are pain receptors, essentially are some kind of nerves which essentially send sensation of pain to your brain. Yeah, so uh, yeah, here it released and it released here. So that's the difference between the conventional needling and the micro needling. So yeah, it's inspired from mosquitoes. So yeah, it quite injects quite easily without much. So yeah, the place where it injects also is not much invasive. So yeah, it's a nice method to have something injected onto the body. So surface forces are important in microsystems compared to macrosystems because, so these are some options. B. Okay. Others, what could be the answer? Yeah, perfect. So the answer will be area by volume ratio is larger in microsystems compared to microsystems. Yeah. So these uh, these surface-based forces and bulk forces is something that essentially um, determines a lot. Like it makes a lot of difference when we are fabricating our devices. So, like for example, uh, in bulk, yeah, when you have higher volume, like in bulk materials, the role of gravity essentially is very high, yeah. But when you go down to micro and nano scale, the because we have very low volume and high surface area, the other forces like the friction and the forces like electrostatic force and um, some other like friction and what some magnetism also affects a lot, yeah. So that's the thing, the gravity based forces are less and surface based forces are more. So yeah, that's the logic here. So that's why when you are scaling down the factor, like scaling down your devices, there's a challenge in understanding what the like how it will behave differently from the bulk interfaces. Because then like when you have gears in essentially gear in macro scale, or you make gears in gears in macro scale and you have gears in micro scale, because there the forces of friction will be much more dominant than the effects of gravity as such. So that's kind of a uh, scaling factor, scaling analysis that has to be done before scaling down. Essentially, is one of the important studies of fabrication. So yeah. So essentially, all this was all we had for this week. Essentially, I have divided. Essentially do the course in a this problem solving sessions in a way that first half an hour is kind of a discussion on what the week was all about. Then we have around 1 hour of questions, and rest half an hour is based on the doubts of yours. So whatever if this combination is good for you, just yeah, you otherwise you can tell me, then we can just shift it away like however you want. So that's the way. So essentially, if you have any doubt from week 1, we can discuss this. So yeah, I'll be there for some time, and yeah, if you don't have any doubts, you are free to leave. So uh, which week are you solving currently? Are you all solving? Is it week 2 or week 1? Okay, you all are solving week 1 now, yeah. Okay, yeah, perfect. So yeah, and what's the deadline for submission? 9th. Okay, so yeah, you have quite a lot of time. So I think yeah. So if you have any doubts currently, you can ask. Otherwise, yeah, we're good to go. Sure. Okay. Thank you all. Thank you.